Hello, the topic of today's lesson is graphs of functions. We are on page 26. Let's read the word problem. Dylan is 3 years older than Ellen. Well, we do know that every time Ellen has a certain age, Dylan will be plus 3. Plus 3. Dylan will always be 3 years older than Ellen, given from the problem, and Ellen will always be 3 years younger. When Ellen was 1, so if Ellen is 1, then Dylan is 4. If Ellen is 2, Dylan plus 3 will be 5 years old. And if Ellen is 3, Dylan will be 6. The rule for this relationship between Ellen's and Dylan's age is x plus 3. Now, look at what we can create. We can visualize the relationship between their ages by plotting Ellen's age and Dylan's age on a coordinate plane. Take a look. If we use Ellen's age as x and Dylan's age as y, notice Dylan's age will be plotted on the y-axis and Ellen's age will be plotted on the x-axis. Here it is, Dylan's age and Ellen's age. Let's construct a visualization of this relationship between Ellen and Dylan. So when Ellen was 0, Dylan must have been already 3 years old, plus 3. When Ellen is 1, Dylan was 4. We can create x, y value pairs, and we can plot them on our coordinate plane. When Ellen is 4, Dylan is 7. 4, 7. Remember, the first value is x and the second is y. So the rule for this linear graph is y equals x plus 3. Excuse me. Let's take a look and answer some questions. When Ellen is 9, when x equals to 9, how old is Dylan? Well, step 1, let's go up to the graph until we hit the graph. And then let's go turn around, turn left, and see. Using the graph, we've determined that Dylan will be 12. Of course, we could identify this automatically, mathematically 9 plus 2, but we're practicing to use the graph to find the solutions. From the graph, find the value of x. Again, solve for x. Find the value of x when y equals to 8 and y equals to 10. So let's see. When y equals to 8, right? This is y. Let's go to the graph, found the point, and go down to the x-axis, which is Ellen's age. Then, of course, Ellen has to be 5. And also, when y equals to 10, when y equals to 10, just like here, y equals to 8 or 10, let's use the graph. Let's use the graph. So when y equals to 10, we go all the way to the graph and then find the corresponding value of x, and it is 7. X equals 7. This is an example of how we can use graph to solve an equation or solve for x graphically. We solve for x using graph. Using graph. Very important. Today's topic, we're learning the relationships between x and y as they follow a specific rule, like y equals x plus 3, and we're using a graph to solve for x or to solve for y. Now, let's take a look at example number 1. Study the graph. Well, first of all, we see that the graph is a straight line starting at the origin, and typically lines go on forever. So it starts with 0, 0. And we see that the rule for this line is y equals 2x, or double the x. So look at the instructions. Use the graph to solve for x. Remember, we're not using a different method we learned last week about isolating the variable. We're using the graph. My friends, just for you to kind of visualize it, these are the values for y. X goes in, gets doubled, and out comes the y. So let's see. If 2x equals to 6, let's find 6. Here it is on the y-axis. We go to the graph and drop down. We know x must be equal to 3. Next, for y to be equal to 10, here it is, y is equal to 10. We go to the graph. Once we find the intersection point, we drop down to the y-axis. X must be equal to 5. When y equals to 7, here is 7. We go all the way to the graph, drop down to find our x, and we know that x equals 3.5. And when y equals to 0, x is 0. Here is this point, right? So let's continue this exercise. Look at the instructions. For 2a, use the graph to solve for x. Use the graph to solve for x. So let's take a look at the next example. Again, we are given a graph. And this graph is again a straight line. I probably shouldn't use such a fat marker. Let's use a pencil. This graph is a straight line. Okay, and look at the rule for this graph. The rule is always the most important thing. How do we generate the values? So think of it as a little function machine, right? Like a little calculator. So in goes your x, certain values, and out comes a y. And what's inside? We triple the x and subtract 2. That's the rule. For any x that comes in, that's how we generate the value of y. So again, we have few equations. 3x minus 2 equals 4 equals 5 equals 6. Let's solve for x. I want you to visualize something like this. These are our y's. These are the outputs, right? Y is your output. And x is your input into our little machine. So what happens when y is 4? Which value of x? Let's go backwards. We don't need to use algebraic manipulations. We just use the graph. So when y equals to 4, we find y equals to 4. We navigate towards the graph. We drop down. X must be equal to 2. When y equals to 5, that's the next question. Here is y equals to 5. We put our eyes to the graph. We drop down to the x-axis. X must be equal to 2 and 1/3. When y equals to 6, what happens? The graph keeps increasing, right? The x values are increasing, not by much. This must be x. Corresponding x is 2 and 2/3. We solved for x using a graph, using the visualization. Next question, what are the possible values for k? This is confusing to students sometimes. I wish they didn't use this language. If the solution to 3x minus 2 equals k is an integer, we know integers are positive or negative numbers, including 0, but there must be whole numbers. So 3x minus 2, what can be? Let me pick a different color. Can be something like 11, right? So take a look. If 3x minus 2 equals to 11, what are the possible? Yeah, this is our value. And in this case, the input x would be 4 and 1/3. That's one example. Another example for k can be another integer. Let's say 15, right? 15, somewhere up here. Hi. Let's go to the graph and drop down. Well, if 3x minus 2 equals to 15, we know x must be 5 and 2/3. Notice, my friends, how we're using graph to solve equations. In other words, we solve equations with a graph, not algebraic manipulation. One more example, number 3. We have a very steep looking graph. Step 1. What do we notice about this graph? That it is also a straight line. My friends, not all graphs result in straight lines, but so far, this is what we see, the examples we see. We also have the rule. This is the rule for the graph, right? This is how we generate our outputs based on inputs. Imagine this function machine, and in goes some values of x, different ones, and out come the values of y. And what happens inside the machine? We double the x and subtract 1. So remember, y's are called outputs and x's are inputs. And we can plot them, outputs. So let's solve these equations. Remember, using a graph, not algebraic manipulations. Okay, so when y equals to these following values, if y equals to 9, let's find 9. Here is our 9. We go to the graph, we drop down to find the corresponding solution, then x must be equal to 5. Next, if y equals to 4, here's y equals to 4. We go to the graph, we drop down. It looks like x must be 2.5. We solved equations using the graph. Write an equation that can be solved using this graph. Well, we know the equation, the rule is 2x minus 1 equals, well, which possible values of y? Let's say that it's maybe 11 equals 11, right? So let's solve it. Let's pick up a different pencil. This is our 11. Let's go to the graph and let's drop down to find the corresponding value. X must be equal to 6. Another equation would be 2x minus 1. Let's see which value can we pick. Some integer, some nice integer. 17. I like 17. Right? Here it is. Let's go to the graph and let's drop down. Let's drop down. X must be equal to 9. We solved two equations